Okay, so in the previous video, I explained why we considered a simple example of survey asking income. And we learned what is random and what is not. And in the end, we learned X bar is random. And as I said, when something is random, we can calculate probability, mean, and variance for the random object. In the end, today, in this chapter, we are going to calculate the probability distribution of X bar. So that is the goal of this chapter. So to do that, let me fix the notation first. A random sample is, in statistics, more rigorously is a collection of observations denoted by n number of like x1, x2, n xn using the subscript, and the subscript denotes the order of observations or order of realizations, but it doesn't matter. Just what matters is you have n number of observations, right? Or like you have, so n denotes the size of the sample size. And in statistics, we like when you say something is a random sample, then it means it satisfies these two assumptions. Assumption number one, identical distribution. That means all the observations should have the same distribution. Like so, that means the parameters are same and they are from the same thing. For example, think about this way. So there are, like you observe 100 numbers from 100 repetitions of dice rolling. You roll a dice 100 times and you collect the numbers. Then they are identical distributions. But suppose that for the first 50 times you roll a dice, and for the second time, instead of rolling a dice, you toss a coin. And then, of course, rolling a dice and like a coin toss are different distributions. So, like collecting just anything does not make a random sample. They must be from the identical distribution. So, identical distribution assumption is obvious and yeah, pretty mild. In most cases, data are of the same nature, so you can think they are from the same distribution. And assumption number two is the statistical independence. That means the first observation does not affect the result of the second one, right? So all the observations are independent of each other. And like as I said, one does not affect the other, and so we studied independence in chapter 2. So the same independence is assumed here. And also we used the independence again in chapter 5 about binomial distribution. At that time, we also assumed independence. So like if you think about coin toss, if you toss a coin and then repeat that, then you know no matter what the first outcome is, always the second outcome is half and half. The randomness in the second one is half and half, does not depend on the first outcome. So it's an example of independence. So a random sample is identically and independently distributed random variables, right? That's also, and throughout this course and most of the statistics, we call this, combining these two assumptions, we call them i.i.d. So identically and independently distributed. i.i.d. assumption will be maintained, even if I don't assume that, but they are going to be maintained throughout this course, right? And as I said in the previous chapters, I considered a single observation, single experiment. So the structure is like this. There is one experiment and it generates one observation. And you repeat that experiment many times, then you can study the distribution of x. You can calculate probability, you can calculate mean and variance. So basically, the theory was coming from this structure, which is pretty simple. And as I said, we are going to change our concept and we will think survey as one experiment. However, still, we can imagine hypothetical repetition of the survey. So, one experiment, so in our setup in this chapter, a more large-scale experiment generates a random sample of size n. So a survey generates 1,000 observations at a time. Still, that is one experiment. We call this as one experiment. And not a big problem because anyhow, we are going to summarize 1,000 observations into its average. Just into one number again, back to one number. That means, so large-scale experiment is actually one experiment, and its result is x bar. Intermediately, there is in between the result and the experiment, we can think of like 1,000 answers, but actually just one experiment results in one outcome. So there is no difference in terms of the structure. Just there, it just involves calculating the mean after the outcomes are realized. So survey is the experiment and the average is the outcome. One experiment, one outcome. So everything is the same, right? And then, as I said, the outcome is the sample mean. We learned it is random. So we are going to study its distribution. This distribution is coming from repetition of the underlying experiment. And the underlying experiment is survey, right? So I believe you understand what I said here. And now, you have to imagine what is the experiment, what is the repetition, what is the outcome, and what is the distribution. Here, the experiment is the survey. The outcome is the average income out of the survey. And we repeat the survey. Repeating the survey is choosing another set of 1,000 people. And then, if you repeat that again and again, then each time the calculated average income would be different. So you are going to have some kind of distribution of them. That is what we are going to do, right? So this is another way to explain this. So previously, as I said, choosing 1,000 people was understood as repetition of 1,000 experiments. But now we will consider 1,000 people as one experiment. Then what is the experiment? You have to imagine another research center. So research center A chose 1,000 random people. And then there is an independent research center called B. They choose a different set of 1,000 people at random, right? And there is another research center out there, C, D, E, F. So in that way, one research center is doing one survey, that is one repetition. And another research center repeats, another research center repeats. So in that sense, if you can imagine 100 research centers, then you are observing 100 average income. So different research centers like report slightly different values of average income, and that difference is coming from the randomness. This is the situation we will study. So, right? Again, so you see it now. I hope you to see. I want you to see the difference. 1,000 here is not the repetition, and this 100 number of research centers is the number of the repetition of the experiment that we are interested in. However, like in the end, they are related. This repetition and this repetition are related. So then we call this sampling distribution. So the sampling distribution is the distribution of the outcome from a large-scale experiment. So like large-scale experiment itself is actually repetitions of a simple underlying experiment, but but we understand the large-scale experiment as one experiment, and then if you could repeat that large-scale experiment, then you will obtain a new distribution called sampling distribution. So the distribution across 100 research centers will be sampling distribution. This is different. So and we are going to calculate the mean and the variance of x bar and the probability distribution of x bar. And x bar is, again, the average calculated from the sample, right? And actually the main reason why it's confusing is because of its name. X bar is on average, which is a sample mean. You calculate the mean from the sample, so it's called sample mean. But I said I'm going to calculate the mean of the sample mean. Mean of the sample mean? Yes. Actually, I had to say of the population mean of the sample mean. So, what's important here is not the name. Name is mean. So there is a sample mean and there is a population mean. They are different things. And the sample mean is random. That's the important point. And I said a random thing has a mean. So sample mean is random, so it has its own mean again. Now, so I'm going to call this expectation of sample mean. That will be more convenient. Will prevent like unnecessary confusion. So expected value of the sample mean is the population mean of the sample mean, right? And to understand this, this is confusing, so don't worry too much about the name, but please imagine this scenario. If you see what is randomized and what is repeated, what is observed, then actually it's not much complicated. But once we write down and read it, like when I ask you a question, what is the mean of the sample mean? Then it starts to be confusing. So I would like to call it this way. Instead of sample mean, I'm going to avoid mean if possible. I'll try to avoid mean, like keep it as a neutral term. And I will call x bar, sample mean, as an average, so that it sounds more like it's calculated from a lot of numbers. Average is more like tangible numbers. On the other hand, I'm going to call this the population mean as the expected value, because expectation sounds more like mathematical, statistical, theoretical. So I will usually call this the expectation of the average instead of the population mean of the sample mean, right? So this is this is a brief explanation why it is confusing. So, but actually it doesn't need be. Okay. I will continue with a simple example in the next video. So I will show you some simulation results. Okay. Okay. See you later.